Hello again and welcome to the third video here in the series on uncertainties. Today we're going to be looking at combining uncertainties. The outcomes for today is you need to be able to calculate the overall percentage uncertainty in a quantity if it has both random and reading uncertainties, or if we have uncertainties in multiple quantities. However, it will require you to have a little bit of prior knowledge. You need to be able to determine the reading uncertainty in a measurement, calculate the random uncertainty in a measurement, and to convert from absolute to percentage forms. If you don't know how to do that, I strongly suggest that you go back and have a look at the previous two videos. They'll explain how to do that. So, let's crack on to combining uncertainties then. The key to combining uncertainties is in being able to calculate the overall percentage uncertainty. Let's say we conducted an experiment. We took multiple readings and they were all different, therefore we had a random uncertainty. Averaging those times together gave us 1.56 seconds. Using a digital stopwatch, that means we have a reading uncertainty of 0.01 seconds and a random uncertainty of 0.06 seconds. So the question becomes, what is the overall uncertainty in the time? Well, to do this, we need to convert both the reading uncertainty and the random uncertainty into percentage uncertainties. Converting the reading uncertainty, it becomes 0.6%, and the random uncertainty becomes plus or minus 3.8%. Having done this, we can see that the 3.8% is larger than the 0.6%. This becomes our dominant uncertainty, and this becomes the overall uncertainty in our time. We could then state that the time is 1.56 seconds plus or minus 3.8%. Converting back into an absolute uncertainty, it gives us 1.56 plus or minus 0.06 seconds. But Ninja, you handsome rogue, I hear you asking, if we're just going to pick the largest percentage uncertainty and make that our overall dominant uncertainty, why did we have to convert into a percentage uncertainty in the first place? Couldn't we just have picked the plus or minus 0.06 seconds? Well, in this particular case we could have, but in most examples we can't do that. To illustrate this point, I have an example here for you that I will go through. A pupil's trying to calculate the voltage of a power supply. She connects it to a resistor of known value and measures the current through the resistor. She then uses Ohm's law, V equals IR, to calculate the potential difference across the resistor. She obtains the following experimental values. R equals 150 plus or minus 10 ohms, I equals 0.1 plus or minus 0.01 amps. The question then asks us to calculate the potential difference across the resistor and the approximate absolute uncertainty in the potential difference. Let's start with question A. To calculate the voltage across the resistor, we multiply the current by the resistance, 0.1 times 150, to give us 15 volts. Part B is where we have to combine these uncertainties to find the overall uncertainty in the potential difference. This is where we can't simply pick the largest number. To ask if 10 ohms is larger than 0.01 amps is the same as asking if 10 seconds is larger than 20 pounds. We can't simply compare the size of the numbers when they have different units. This is where it becomes important to compare the percentage uncertainties to find an absolute uncertainty in the potential difference. And so we have to find 10 ohms as a percentage of 150 ohms and 0.01 amps as a percentage of 0.1 amps. Converting them into percentages, we find that the uncertainty in the resistance is 7%, whereas the uncertainty in the current is 10%. The uncertainty in the current is dominant. It's larger than the uncertainty in the resistance, and so this becomes our overall percentage uncertainty in the voltage. And so our voltage becomes 15 volts plus or minus 10%. The question asks us for the absolute uncertainty and the potential difference, not the percentage uncertainty. And so converting back to absolute, we find 10% of the 15 volts, and we get 15 plus or minus 1.5 volts. So now that I've showed you an example on how to do this, let's do some together. I've got a few here. The first one's from the 2017 exam paper. The link to that is on the screen. There's an experiment that's based around momentum and impulse. Don't worry if you haven't covered momentum and impulse yet. That's not important for here. What is important is being able to handle the uncertainties. A cue with a push switch hits the ball and starts a timer, and the ball moves towards the motion sensor, which is connected to a computer, and there are results taken. You can see we have a time, a speed, and a mass. The first question asks us to calculate the average force exerted on the ball by the cue, and the second question asks us to determine the percentage uncertainty and the value for the average force on the ball. Let's have a look at the first part of this question. Like I said earlier, if you haven't covered momentum and impulse yet, don't worry about it. You're more concerned with the next question. However, maybe you're watching this and you have covered it. If that's the case, pause the video, have a go at the question. To calculate the average force, we're going to use Ft equals mv minus mu. The force multiplied by the time is equal to the mass multiplied by the final velocity minus the mass multiplied by the initial velocity. Substituting the time, the mass, the initial and final velocities in, we find that the overall force is 3.8 newtons. Part 2. Calculating the percentage uncertainty and the value for the average force on the ball. From the equation, in order to calculate the force, we need to use the time, the speed, and the mass. We need to use all three of these values here. Therefore, we need to combine all those uncertainties, the uncertainty in the time, the uncertainty in the speed, and the uncertainty in the mass. If you think you can do it, pause the video and have a go. Okay, in order to combine all these uncertainties, like I mentioned earlier, we need to convert them into percentage uncertainties. The percentage uncertainty in the time is 0.001 as a percentage of 0.040. We find this to be plus or minus 2.5%. 0.01 meters per second as a percentage of 0.84 meters per second becomes plus or minus 1.2%. And 0.001 kilograms as a percentage of 0.180 kilograms becomes plus or minus 0.6%. We can see that the 2.5% is larger, and so is the dominant uncertainty. This becomes the overall uncertainty and our final value, the force. The second question I would like to go over is from the 2018 exam paper. Again, the link is on the screen if you want to go to the website and download it yourself. It comes from question 20 of the multiple choice section. A student carries out an experiment to determine the specific heat capacity of a solid. You should have come across this equation in National 5 Physics. C equals E over m delta T. We can see that we're given percentage uncertainties already in the energy, in the mass, and in the change in temperature. And we have 5 possible percentage uncertainties in C. I'll let you pause the video, have a think, and see if you can come up with an answer. So this one's more straightforward than most. In fact, it's already done the percentage uncertainties for us. All we need to do is pick the largest one. We can see that the largest percentage uncertainty is 5%. That's the change in temperature. And so that becomes the dominant percentage uncertainty. That becomes the percentage uncertainty in C. So it's answer C. The last example I'd like to go over is from the 2019 paper. Once again, the link's on the screen. Go and download it, have a shot. Again, it's from the multiple choice section, question 22, and this one's slightly more difficult. A student sets up a circuit, measures the voltage across and the current in a resistor. The measurements and their uncertainties are, and it displays them. It asks us for the approximate absolute uncertainty in the calculated value of the resistance. I'll pause the video here. Please have a go. So let's go ahead and calculate the resistance first. To calculate the resistance we use Ohm's law, and rearrange for the resistance. We get R equals V over I. This gives us 10 divided by 0.5 or 20 ohms. But what about the uncertainties? Well, we need to combine the uncertainty in the voltage and the uncertainty in the current. To do that, we need to convert into percentage uncertainties first. 0.1 volts as a percentage of 10 volts becomes plus or minus 1%, and 0.01 amps as a percentage of 0.50 amps becomes plus or minus 2%. This means the uncertainty in the current is dominant and is our overall percentage uncertainty, plus or minus 2%. However, the question is asking us for the absolute uncertainty, not the percentage uncertainty. This means that we need plus or minus a certain number of ohms. Overall, our resistance is 20 ohms plus or minus 2%. Finding 2% of 20 ohms gives us 0.4 ohms. So our resistance is 20 ohms plus or minus 0.4 ohms. The answer is C. I hope by now you've had some insight into how to combine uncertainties together. Maybe you have a reading uncertainty and a random uncertainty for one particular measurement. Or maybe we have an uncertainty in 2 different values and we need to combine them in order to find the uncertainty in another quantity. I hope you've learned something from this lesson, and until next time, take care. Bye.